everyone. So I'm Ujjwal. I'm a PhD student at Berkeley and also leading this project called Specular. And I'm just going to really quickly cover some security risks in EVM-based optimistic rollups today, and what we're trying to do to address these issues. Right. So if you kind of look at the existing landscape, the state-of-the-art kind of...
Sorry to interrupt. Can you please stay?
Yeah.
Thanks.
Cool.
It's all getting recorded, otherwise we lose.
Got it. Yeah. Right. So if you look at the state-of-the-art, they kind of take one specific approach, which is you take the client implementation, you compile it down to some lower-level virtual machine, and then you prove the execution of that binary at that semantic level. So there's like a bunch of issues with this that I can't cover in 4 minutes, but essentially one of the key problems here is that it's very difficult to reason about the semantics of the system because the proof system is essentially enforcing the semantics of some lower level virtual machine and not what that binary is actually implementing. So if you want to get some formal guarantees about the system, that's very difficult to do. Especially because like the TCB actually includes like hundreds of thousands of lines of code. You have the execution layer client, you have the compiler and so forth. So it's just like very infeasible to get formal guarantees about that. And so what we've been focused on is essentially designing a proof system that targets the higher level semantics directly. And so the nice thing about this approach is that it allows you to distribute trust through what we call like one-of-n version programming and shrink the TCB to something that's like more manageable and you can formally reason about. And this kind of like eventually amounts to formally verifying an EVM instruction emulator that's written in Solidity and compiled to EVM bytecode, which is like kind of weird if you think about it. But what that gives you is like the ability to get some formal guarantees about the proof system that you have. And so that's kind of what we're looking at doing now. So we're using the Daphne EVM specification and trying to leverage Daphne to essentially get some or prove the correctness of the YUL code that you get from compiling the Solidity contracts that implement the verifier, and then basically prove some refinement relation between that and bytecode that you would get from compiling directly to EVM bytecode, and through that get some formal guarantees of the system's correctness. And yeah, so this is kind of work in progress, and we're going to publish a blog post soon. But if this sounds interesting to you, happy to chat about it more later. I don't know if that was, but yeah, that's about it. Thanks.